will start. Okay, I think it's great. Okay, should we get to go?
Cool. So I can start talking. It's are
Yeah.
you guys ready? All right, nice. Cool. So hi, I'm Pierre. I work at PSE, and I am developing Sonobe, which is a folding schemes library with Arno Cube, with working with Zero Spark. And today I'm going to try to make like two things. So there are two goals. The first one is to give you like an overview of what's IVC and folding schemes. And I think the audience is like there is some variance in the audience with respect to how familiar people are with folding schemes. Some of you are like super familiar with them and understand like what's going on. Some of you guys don't really know what it is. So I'm going to try to like um, um, make it possible for everyone to be happy at the end of the workshop. So how I'm going to proceed is that first I will give you like an intro to folding and the applications that you can do with folding to give you like a sense of what is it and what you can or cannot do with it. So it will be a bit like a broad introduction, um, giving you like bits and bytes of small theoretical bytes on where you can go to start reading papers if you want to, but also actual practical stuff that you can start doing today. So yeah, that will be the first part. The second part then will be about like simple folding application with Sonobe, so a very simple circuit. And the idea is just to walk you through like how it works and what's the like the paradigm that you need to have in mind when if you want to start to program with Sonobe. So I'm a bit bearish on this part, if I may say, because I don't know how familiar you guys are with ArcWorks. Today, right now the circum support with Sonobe is pretty much limited. So we will be doing the example with programming R1CS with ArcWorks. But like if you are familiar with R1CS programming, I think you will be able to follow through. It's just that we won't be using circum, but circum support should soon be ready in Sonobe, and it should give you like the mindset of how Sonobe works and what you have to do to make it work. Cool. So I was afraid that you guys would not be here this morning because I know that you were having a birthday party yesterday, I think. So happy birthday to the hero that I can see with his glasses. So happy birthday to you. And yeah, now that we have the program out of the way, let's start. So I'm going to start to share my screen. Cool. Can you see my slides?
Yes.
Cool. And effect. All right, cool, perfect. Okay. So yeah, the title says it all. It's a brief introduction to folding and its applications. Okay, so what we will do is we'll have a 6-part presentation. The first one will be dedicated to the concept of incrementally verifiable computation. It's a concept that you will often see pop up here and there in the literature, and I will try to give you an understanding, the motivation and the understanding between the concept of incrementally verifiable computation. Then I will introduce you folding schemes. A folding scheme is actually a very simple cryptographic scheme where the idea is that the prover will want to convince a verifier at its most basic level, that he knows two satisfying witnesses to an R1CS. Folding will then make it possible for the prover to prove that very efficiently with respect to the verifier. Very efficiently in terms of like communication costs, and also in terms of like computation costs, because it will be done with a single witness. So then I will show you a bit also what NOVA consists in. So NOVA was the first, so it was the paper that first introduced folding scheme, what a folding scheme is. So it was written in 2021, and it was also the first paper to make it to achieve IVC using a folding scheme. So that makes NOVA like the must-read paper if you are interested into like folding schemes and IVC in general. And I will and the paper is not like super easy to grasp at a first read. So I will try to make it possible for you to get an intuition of the main idea behind how NOVA works. Then I will also make you a brief overview of the different schemes that have been proposed after NOVA. So I call that beyond NOVA. So it's mainly schemes that are like for Plonkish circuits, or also making it possible to not only fold two instances into one, but n instances into one. And also like post-quantum secure IVC schemes using folding, such as lattice fold that was out not too long ago. Then I will also walk you through finally the different applications and make a first touch about what Sonobe is. Okay, so we have some stuff to go through ahead. So let's start now. Cool. So let's start with what IVC is. So the question that is asked by the guy that first talked about IVC with Paul Valiant in 2008 was he asked this very simple question, which was that he supposed that for some regular computer, he asked himself whether he could turn this computer into a new one, which would frequently output his current state along with a proof for it. So it's very similar to the idea of basically a provable VM, in which for which the VM would output a computation trace and maybe make some proof about that specific computation trace, proving that the trace is actually correct. And so here it's basically the canonical question, which is, can you turn any regular computer into a new one, which would frequently output its current state? So think about, for instance, the state of its memory, along with a proof for it. So actually proving the different transitions through which the computer has gone through with respect to his memory states, say. So it's very relevant, for instance, when you are outsourcing computation to cloud servers. It would make a lot of sense to have such kind of proof. And it makes also, in general, it makes sense when you are delegating computation to an interested party to have an actual proof that this interested party has computed the thing that you have asked him to compute correctly. So this is the initial question of IVC. And it gives Paul Valiant two motivations for IVC, which are very interesting from a philosophical point of view. The first one is a human motivation. And he asked whether it would be possible, and if so, how, to perform computations spanning over multiple generations. And it would be the case, for instance, let's say that you have aliens coming in 400 years, and you need to make a very long computation, and that computation is going to span over multiple generations. The question that he asked is whether you can, for instance, first, let's say, checkpoint the computation so that if it fails, then you can continue the computation where it's stopped at with a proof of where it stopped at, and make it possible for future generation to continue that computation that you have started. So there is like this human motivation in general. And there is also a computational motivation, a computational setting, which is more generally to ensure that the computer that you have delegated computation to is doing the required work as expected. So this is the idea of delegating computation to interested parties, which is the idea of in the blockchain setting of rollups, of the general paradigm of scaling today. Okay, so the entry door that has been taken to achieve IVC in the beginning is to say that we want to leverage the fact that we are going to perform repetitive computation, and the fact that we are doing repetitive computation is an advantage in terms of how to tackle this problem. So the thing that we want to do is leverage the underlying structure of repetitive computations to make it possible to output the different states through which the computation is going to go through. Okay, so in which kind of settings do you encounter that? Well, you can have a model which would infer on thousands of different data points. Or you could have a VM with a fixed set of opcodes. Or you can have rollups which batch verifies signatures. It's always the same computation again and again. Same for a blockchain consensus. It's always the same consensus algorithm that is applied again and again. And so that's why the applied crypto world has been very interested into leveraging snarks to do this, because there is like a lot of problems that are actually embodied by repetitive computation. And so it's interesting because it's unlocking a new design space for on and off-chain apps, such as like coprocessors. So we have heard a lot about this in the past few months, ZKML, ZKVMs, etc. And so that's the little formula on the right, where you start from a state S0 and you apply n times the function f, and you end up with the state n. And so the naive route to do that would be basically to just prove the unrolled statement that you are making. So let's say, for instance, that you want to verify 100,000 signatures, then the idea would make to just make a for loop from 0 to 100 and every time verify the signature. But there is a kind of a problem with that. The first one is that you need to fix n ahead of time. So here, 100,000 signatures. So if you have, for instance, a circuit on which you are going to do a trusted setup ceremony, it's not very useful to do that. And then also the prover memory would be dependent on n, because you have the circuit that the verification circuit for the signature that you have, and you are going to run it n times, so it's going to be n times the size of your circuit. So it's not very interesting in terms of scaling. And the verifier time may also depend on n in some settings. But yeah, in general, the naive route for snarking repetitive computation is not that interesting. And that's the little drawing that you have on the right. So you would repeat f in the same circuit, in the same arithmetic circuit, n times. So your arithmetic circuit in terms of prover requirement would be n times f. So it's not very useful to do it this way. So what we want to achieve instead is to be able to not fix n ahead of time, to have prover memory that is only dependent on f, so the size of the circuit that you want to repetitively execute, and have verifier time not depending on n, ideally. So that's now the little drawing that you have on the right, where you can see that each of the execution of f are happening not in the same arithmetic circuit of all the other ones. So those are like separated execution of each other. So, and you see that there is a state that is going through each of those execution of the circuit F. So it starts at Z0, it goes into F, then it outputs Z1 that gets into F as well. And you can see that you have also auxiliary inputs, so the witnesses, W0, W1, that can go into F. So it's a very different setup than the previous one, where F was all the executions of F were into the same big arithmetic circuit. So it's possible to do that. And how we are going to do it is using a folding scheme. So that's going to be now what we're going to discuss. Okay, so what's a folding scheme? So this term was coined within the Nova paper in 2021. And it's literally the formula that you have on the right. It's the main insight that was proposed by the paper, which is that if you have two satisfying witnesses for a specific R1CS instance, then a linear combination of those two witnesses would also satisfy this same R1CS instance. Theoretically, of course, because we need to make adjustments to that. It does not work like straight out of the box, but I'm going to walk you through of what you have to do to have this possible. So the intuition is straightforward. If you have two witnesses satisfying a particular R1CS, a random linear combination of those two witnesses will result in another satisfying unique witness. So here we require the linear combination to be random because it will be an interactive proving. It will be an interactive proving scheme between a prover and a verifier. So the verifier will basically send some randomness to the prover. That's why the linear combination is a random linear combination. But of course, it would also work if your little R term is not randomness. But in that case, it would not be cryptography anymore. So. Okay, so there are three ingredients to the folding scheme that was proposed in the Nova paper. The first one is what we call relaxed R1CS. And that's the first equation that you can see on the right. And it's slightly different from the canonical R1CS equation in that it introduces, you can see, a little U term and an E term. So it's an adapted version of R1CS that makes it possible to take a linear combination of witnesses and have this linear combination to still satisfy the original R1CS equation that you have. Then the second ingredient is the random linear combination idea. So to take linear combinations of witnesses. And finally, it's the homomorphic commitment scheme to hide witness values so that the verifier does not know what is the content of the witness. And to do that, you not only need a commitment scheme, but you need that commitment scheme to be homomorphic so that you can actually take linear combinations of those two witnesses and still have this committed linear combination of witnesses to satisfy the original R1CS instance. So that's the three main ingredients of the folding scheme: the relaxed R1CS, the linear combination of witnesses, and the homomorphic commitment scheme. So, yeah. An interesting fact was that Nova was not post-quantum secure because, as far as I know, you don't have a post-quantum secure homomorphic commitment scheme. But recently, there was the lattice fold proposal, which is a different setup than Nova in general, but which is a post-quantum secure folding scheme. So yeah, it's an interesting fact too. So. Okay, so now that we have those three ingredients, we can have the folding scheme protocol ready. So here is the simplified protocol, how it works. So it's very easy. So this is interactive between the prover and the verifier. You can make it non-interactive using Fiat-Shamir. And it works this way. So you will have the prover to commit and so hide to a pair of satisfying witness instances. So I know two witnesses. I hide them by committing to them, and I send those committed witnesses to the verifier. The verifier takes those two witnesses, and then we'll send some randomness to the prover. So this is the little R term that we have seen in the equation. Then both the prover and the verifier will linearly combine the two elements of the hidden pair of witnesses. So this is the equation below, where with W bar is assigned W bar 1 plus R of W bar 2. So both the prover and the verifier compute this linear combination. And then the verifier can check that this linear combination of hidden elements, the hidden witnesses, satisfies the relaxed R1CS equation. And that's it. That's a simplified presentation of it, but that's literally how a folding scheme works. So this is the original protocol that was proposed into the 2021 paper. Cool. All right. So now what Nova will do is take this folding scheme that we have described and use that folding scheme to achieve IVC. So we need to remember that IVC is this ability to output at each computation step the state of the memory of the VM, say, that we have. And Nova is using folding scheme to achieve the ability to do IVC. Okay, so here is the Nova car. Let's say that it's a car, and we are going to check each of the pieces of the car. So the engine and all the small little electronic additional components that make sure that the car is not derailing. So at the heart of the car, of the Nova car, you have the repeated function being run, which is the F function. So this is our original circuit. So for instance, a circuit that checks that a signature is correct. So this is going to be the main function that is being run within the little Nova car, basically. This function is going to output an updated state obtained from running F here. So you can see that you have Zi here and Zi plus 1, which is going to be the updated state obtained from running F, which is the repeated function being run. Then you have also incremental updates of the states, of course, that are done by the function F, but also of a little counter I to check how many times the function has been run. Then you have folded values that end up being accumulated every time, because you are going to successively take random linear combination of witnesses. And so you will end up basically with accumulated folded value. Here you can see that you have something called the NIFS.V, which means the non-interactive folding scheme, the verifier part of it. So within the big Nova car, you are going also to run the non-interactive version of the folding scheme, and you are going to run the verifier, which is going to check that folding has been performed correctly. And then you have also some hashes that are output by the Nova car to just check that folding has been done consistently, with consistency, sorry. So this is basically how Nova works. You have your function F, and you have a non-interactive folding scheme verifier that is checking that folding has been done correctly at each step that the Nova car is being run. There are some caveats to that because the proof generated by Nova is an IVC proof. So it means that this kind of proof is not succinct because it's a proof that is linear in the side of the circuit, and it's also not zero knowledge, because if a verifier wanted to check whether the IVC proof is correct, it would actually need the inputs the prover has used to run the computation. So an IVC proof is not succinct and not zero knowledge. So it's important to understand that. However, also introduced in the original NOVA paper. The author proposed specialized ZK snark for the committed relaxed R1CS, which we talked about, which is the special R1CS version that we have using committed witnesses, and the authors propose a specialized ZK snark for that specific kind of R1CS to prove the knowledge of a valid IVC proof. And this new ZK snark was an adaptation of a Spartan, but is not as succinct as it's succinct, but it's not as succinct as we would like to be if we want to verify stuff on chain. It's not as succinct as the Crow 16 proof, basically. And it's partly because it's a transparent ZK snark. So it's pretty hard to verify those kinds of proof on chain. All right. So there was actually a lot of research that has been triggered by this paper, and now we are going to go through what has been done after NOVA was out. So the main shortcoming of NOVA is that it's for the R1CS arithmetization only. The thing is that today we have other ZK snarks with other kind of arithmetizations that provide lookups or hide aggregate. And the question that was asked was, can we also fold those schemes? Because folding is interesting, but it's only working for R1CS. Can we do it for, let's say, a Plonkish kind of circuits? And a lot of stuff happened in 2023. Many papers popped up. The main goals were to do folding for Plonkish circuits. So it was the idea of Sangria, for which I learned something interesting, which is Plonk means actually bad wine. So the idea was Sangria was like a little joke about Plonk. So Sangria is a folding scheme for Plonkish circuits. There was also folding adapted arithmetizations that started to pop up. That was also the idea of the customizable constraint system, the CCS arithmetization. And also there was some work that was done in terms of improving the asymptotics of relaxed R1CS folding, especially removing the cross-term blow-up. So this is the E term caused by taking random linear combination. And this was the idea of Hypernova, I think, if I'm not mistaken. But the idea basically is to make it possible to not only fold 2 instances, but up to n instances. And so in 2023, lots of things happened. So you had NOVA, then it was in 2031, and then the research that really started to gain pace. So you had the NOVA ZKVM, Sangria, CCS, Hypernova, all in April. So 4 papers in April 2023. The NOVA ZKVM was a project done during the Vietnam residency by Oscar and Carlos and other folks in the 0xPark Vietnam residency. You had also Protostar, Protogalaxy, then CycleFold, then Kilonova, and recently LatticeFold, which is post-quantum secure. And this is a flowchart that was stolen from Carlos Perez talks at ProCrypto 2023. So if you want to dive more into what happened in 2023, this talk is really interesting for that. So it has been in 2023 a very active area of research. So yeah, research for making it possible to fold Plonkish circuit, also to making even more cheap the fact that we are using a cycle of curves and making the cost to pay to use the cycle of curves even less costly. This was the idea of CycleFold. So yeah, lots of things happening. And LatticeFold recently has been using lattices and using lattices for folding. So they actually end up with a post-quantum secure folding scheme. which is, they claim, the authors of the paper claim, is as efficient as Hypernova, which is not post-quantum secure. So it's very interesting things happening right now. Okay, so let's dive into the applications now. So first you have a verifiable ML. So Lyron did a project where he snarkified 512 layer neural nets. So the idea here is not verified training, but verified inference. So you would provide the weights, and you could prove the inference that has been performed by the 512 neural nets that he has. We also did a project where we would snarkify using Nova and Spartan a Connect 4 engine with a reinforcement learning bot, and this was running in the browser. So it was very, very interesting. So here the idea is to do provable inference using folding schemes. Then you can do also verifiable light clients. So here the idea is to prove the proof of work of a specific chain. We did that for Bitcoin, where the idea is to verify the proof of work for whatever number of blocks that you want. And we should be able to land it on the AVM soon. Yeah. So it's also very interesting. For light clients, we also have rollups, of course, which are a natural candidate for this. If you want to prove that a batch of valid signatures is correct, for instance, if you use a friendly curve cycle, it's even more interesting because you can very efficiently verify batches of SecP 256K1 signatures, say. So here, for instance, on the right, you have Nova proof running in the browser of aggregating signatures, and it's aggregating like 4 signatures per second, which is for SecP 256K1 signatures per second in the browser, in my browser. So it's very, very interesting in terms of speed, and yeah, it's pretty exciting as well. ZK-VMs, of course, there has been a few teams that have started to work on folding schemes based ZK-VM. There is the Lurk Labs team. There is also the Nexus VMs team that is led by Jens Gross from the Gross 16 paper. So it's yeah, lots of work also happening on the side of ZK-VMs. Yep, cool. So yeah, so the idea of Sonobe is in all of that was to have some kind of a one-stop shop for doing folding schemes research, both in terms of like pure research, from a pure research point of view, but to make it possible for, let's say, for researchers to implement their new protocol or scheme that they have implemented using folding, but also like for practitioners, if they want, let's say, for instance, to compare different folding scheme, or to try to do a benchmark for a specific R1CS circuit and to check how he could fold his R1CS circuit for a specific application. Sonobe is trying to tackle those kinds of problems. So it's very rough on the edges. It's a very nascent project, and we are only two. Right now, we are only two working on it, but a lot of people have helped us. But yeah, we are not like a big VC team, VC funded team. So we are trying to make it as usable as possible, but it's still rough on the edges. But we are getting to somewhere. Yes. So it's a joint PSC 0xSpark library, and let's see right now just a little bit of example code. Here, for instance, for the verifiable BTC light client, you can see that it is like curve agnostic, so you can use whatever curve cycle that you want. You can use SecP, SecQ, you can use a BN254 Gonkin, you can use whatever curve cycle that you want to use for the specific project that you want to do. It's also use case agnostic. So here it's the R1CS circuit that we are folding, which is a BTC block checker circuit, just checking the proof of work of each of the Bitcoin block. And it's also agnostic to the homomorphic commitment scheme that you are using. So yeah, we have been trying to make it as generic as possible, to make it possible really to even like benchmark the internals of the circuit that you are folding. So maybe you want to try to fold it on different curve cycles. Maybe you want to try different commitment schemes to see the cost that you are paying. Yeah, that's what we want you to be able to achieve with Sonobe. It's also browser compatible. So we did a bit of work on it, but did not have time to really complete it. But we have actually a proof of concept working of compiling Sonobe to WASM and running IVC in the browser. So this is something possible to do. And I have some example code to do it. So if one of you guys want to try that, I would be happy to help him to do it. And yeah, you can definitely contribute and follow the work being done. And I would be happy to help you fold your circuits with Sonobe and to have a look at our issues. But this is going to basically be the next part of this workshop. Cool. Do you guys have questions, maybe?
Yeah. Can you go back to the car slide, the picture of the car?
Yes.
Yeah, I think like something I've always been confused about is like this represents like, you know, the circuit lowercase u sub I plus 1, but then in this case your input to the circuit is lowercase u sub I. And so I'm curious, like, since you're feeding that into this circuit, like how does this circuit size not grow with respect to n?
I'm not sure to see the link with n actually.
Like, are you like, because it seems like this is some sort of like R1CS instance, and you like put this entire instance as an input into the next step. Is that the case, or what are you doing exactly with that?
Yes, exactly. So yes, so you have the U term and the accumulated U term. So what we are doing is fold those terms together, take a hash of those terms, verify that the folding has been performed correctly. So the final thing that you output is an hash and is another accumulated folded term. But the other accumulated folded term is not going to be bigger than the previous one, right? Because folding is like a linear combination of the two terms. So it's not going to be 2 times bigger than it was before.
Okay.
If that's okay.
Yeah.
Right.
What role is like the hash playing here?
Okay, so that's a very, very interesting question. So the hash is basically to ensure consistency, because what you have is that you are folding little UI with big UI, and you output a new big UI plus 1. The thing is that if you were to do another step of folding, you would eventually fold again the same UI values with the big UI plus 1 term that you have just output. So to avoid refolding the same term again within that big UI plus 1 that you have just output, instead of that, they take a hash of the two terms, that the little UI and the big UI initial that were inserted within that circuit. So that's why I say folding consistency. It's to avoid refolding back again the previous value into the new value that has been just output by the circuit. So if you want to check that, you can go here. Wait, I'm just not sharing the right screen. And So this is in the original Nova paper, and they will explain to you that. So this is literally the things that I have shown to you, and this is in this part that you will see what's happening. So yeah, he will explain to you why they need to take that hash of the UI previous instance. Yeah.
Thanks.
Here's a question.
Yep.
So when verifying the recursion proofs of the foldings, can we access the internal output of the IBC lines or ZI from Z1 to Zn-1 or as a public instance, or we can only use the first and the final state of the IBC as the public instance. So only the first and last one is available, right?
Yes, only the first and the last one. Yeah.
So, for example, if we want to use the IBC for the blockchain 10 block validation of the Bitcoin blockchain, and if we want to verify the intermediate block hash or as a public input, so one way is we define the state as the 10 list of the hash, and for each block validation, we the circuit modifies the ith position of the list into its validated block hash, and it results the 10 block hash, each of which is validated by each IBC.
Oh, that's interesting.
Is this does it work?
No, it's not. It's not. So what you're proposing basically is a way to change the way they describe this.
So the purpose is, for example, the problem here is we want to verify the 10. We want to prove the 10 blockchains. We want to prove that some 10 blocks so the prevent shows the 10 Bitcoin blockchains block hash, and prove that each block hash is derived from the valid Bitcoin's blockchain block. And we want to prove that with IBC. However, if we only set the latest block hash as a state that only the verifier can only use the first and the last blockchain's block hash as a public instance. So to solve that, instead of defining the one block hash, the latest block hash as a state set, we define the 10 hash list as a state, and it is initialized as the all zero list. But when IBC function validates the ith index ith block, it's modifies the value in this list at the position I to the actually validated block hash, and in this way, the final output, the final state output will be the 10 list of the Bitcoin blockchain hash. All of them are validated by each IBC. So do you think it is, do you think such system works?
So I think actually I've said a mistake, because in fact it depends if you are talking about like an IVC proof or a zk-SNARK of an IVC proof. If you have an IVC proof, yes, you actually don't need to change this way. You have to send the intermediate values to the verifier. So the verifier will be able to get information about each of the Bitcoin block hash that you have proven, right? In the case of the zk-SNARK, it's usually to lend it on chain, And in that case, what you are going to land on chain is not 850,000 Bitcoin block hash in a single smart contract. So you will need to just to end up with like the starting block hash and the end block hash. So I don't know if that answers your question, Sora.
Thank you. So, in general, if the verifier directly verify the IBC group, or it can also verify the intermediate state, or
Yes.
in the
Yes.
version proof on chain, it can only specify the first and last state.
Yes.
So
yes, because it's
So if the on-chain contract also want to verify the intermediate state, I have to modify the state of the future, or such that we can easily verify the intermediate state from the last state, right? So,
Yes, definitely. Yeah.
thank you.
Yeah. It's like the idea of also, some kind of ZK coprocessor. You would have like the first state, the last state, and you would have, let's say, for instance, another snark that would prove that in between you have some Bitcoin block hash that corresponds to a valid one. Yeah.
Thank you.
Any other question or?
Sorry. So may I also ask the theoretical question?
Yes.
So the numbers are, so my understanding of the number encoding scheme is, it first defines the protocol as the interactive signal protocol, and it converts the protocol. It is converted into non-interactive protocol using a Fiat-Shamir transform, right?
Yes.
So it proves the protocol soundness using the as a signal protocol, or does it prove the soundness in more special way?
I don't remember exactly. I don't remember how they prove soundness. I think it's at the end of the paper. Completeness and yeah, I don't think I can help you on that. So if that's your question regarding the soundness of the protocol, yeah.
Thank you.
Cool. Any other question? No? Okay, cool. So maybe I can switch to show you a bit about like Sonobe. So just to make a few like points clear with Sonobe. So again, Sonobe is still very rough around the edges. So the example of things that you will not find is not stable circum support yet. We are literally working on stabilizing it right now. There is no IVC checkpointing, so you cannot checkpoint the state of your IVC and take the computation back again. It's also something that we would like to do later on. There is also no trusted setup ceremony on the final ETH decider circuits. So we haven't made any trusted ceremony around it because it has not been audited. So no point into doing it for now. And in general, Sonobe has not been audited. So it's even a custom protocol for verifying on-chain. So really like use it as a way to test things out and to research things rather than as a thing to start to deliver things into production. What you will get though is, I hope, a feeling for the power of the Nova IVC. Also a way to start building apps that can actually land on-chain. We are the only framework doing that right now. and also a grasp for how folding could help with your app. Cool. So let's go. I'm going to start to share. Yes, it's Yanis who sent me that picture. Sonobe station. All right. So I'm going to start to share the screen. Yes, I made a little GitHub repo for that. I'm going to send the link into the Meet discussion.
Yeah, then I will share it like in the thanks.
So it's a very, very, very simple example that we are going to go through. You can just git clone and you should be able to then start to cargo test it. I think no cargo run. All right. So I'm going to start with yes. I'm going to start with sharing my screen. All right. All right. Okay, so this is the repo, and I'm going to start with the cargo tunnel. So a few things that you need to know is that we are using a custom version of ArcWorks R1CS, the STD library, because of a few things in the original library, but we will end up merging back with the ArcWorks R1CS library. A second thing to know is that the Sonobe repo is divided into is a workspace divided into multiple packages. So here we are importing two packages, which is the folding scheme package and the solidity verifier package, because we are going to start to learn stuff on chain. Provide the light test features when you are using the folding scheme. It's to avoid you to use the largest Ethereum decider circuit. So when I say decider, a decider is the one that will provide the final Zk-SNARK proof of a valid IVC proof. So this is the idea of a decider. So the Ethereum decider consists into a big R1CS circuit that will prove the knowledge of a valid IVC proof. And the circuit is pretty big. So you want to keep the light test feature on when you are using Sonobe, and that you are testing stuff out, because otherwise it will take a lot of time and surely crash on your machine if you don't have 32 gigabytes of RAM. Also, so yes, you should provide patches for the BM254 library and the Grumpkin curve also. So that's like, if you want to start your project with Sonobe, be mindful of what you are putting into your cargo.toml. And you can, I think you can use that as a starter cargo.toml if you want. Okay, so the main .rs file now. So what we are going to do is define a circuit to be folded, fold it with the Nova plus CycleFold IVC. So CycleFold is an optimization that was proposed to the original Nova cycle of curves construction. Generate a final proof using the decider Ethereum circuit. Generate a solidity contract to verify the proof on chain, and finally verify the proof in the EVM. So yes, that's the workflow that we are going to go through. Okay, so what you need to know when you are using Sonobe is that your circuit will need to implement the F circuit create. So what is an F circuit? So you remember the F function that Nova will run repeatedly. So this is basically the F circuit, which is the thing that Nova will run. When we talk about the augmented F circuit, it's basically all the bookkeeping that is going around your F circuit. So the augmented F circuit ensures, for instance, that the folding has been done correctly using the non-interactive folding scheme verifier. So when you implement your F function, you will need to implement the F circuit thread for that. But you do not need to worry about the augmented F circuit. This is what we provide with Sonobe. We provide we provide an already prepared augmented F circuit that will, in a way, wrap around your F circuit. So this F circuit will need to implement the thread, which means a new method. So relatively easy to understand. It will also need to say what the length of the state will be. So the state, what we call state, is the Z0 and the ZI values. So here, the length of the state will just be 1. So that will be literally just one public value that will go through each of the states of the IVC. And the external inputs length regards the length of the auxiliary witnesses values that we are going to give to the F circuit when we are going to start to fold things up. There is also two important methods to be aware of, which is the step native method, meaning a step that is done natively without using any R1CS arithmetizations, and the generate step constraints that will generate actual R1CS constraints for your circuit. And this is where you are going to define your R1CS circuit. So what it will take is auxiliary inputs. So the set of already allocated witness values, the ZI state, so a set of already allocated as well public input values. And what you will need to do in that method is here define what you do with those external auxiliary inputs and with the ZI. So for instance, what we do here, we allocate a new constant. So it's okay because it's not a witness value. We also make a copy, we clone the original initial ZI value, and we return within the state the cube of that value plus this value and 5. So it corresponds to ZI cubed plus ZI plus 5. So that's what we are returning. And this is the F function that we are iteratively applying. So if I give, for instance, ZI 0, I will end up, so if my Z0 is 1, the next value that I will get, so ZI plus 1, will be 7, because this will be 1 plus 1 plus 5. Okay, so this is the F circuit thread. Is everything clear for you guys for now? Or?
Yes.
All right. So yes, this is written all with ArcWorks. So the DevX, if you don't know ArcWorks, can be a bit rough, but writing circuits with ArcWorks is actually, I think, more readable than writing circuits with Circom, because it's much more expressive. Circom is sometimes you don't know what's going on with Circom. With ArcWorks, I feel that it's you know much more what's going on. So I'm pretty sure you will be able to do it really quickly. So here that in the main function, we will specify the number of steps that we want the IVC to run with. So we start with the initial state, which will be Z0. So we define it to be 3. We also have our cubic F circuits that will run. So it's just a simple struct that we have here. And once we have done that, we can initialize the IVC and the parameters for the final decider. So in general, that just means initialize the homomorphic commitment scheme that we want to use, and also initialize the parameters of the final decider, which in the case of Ethereum will be a Groth16 plus KZG. And so we initialize all those parameters here. And we can basically just say to Nova that we are using G1 and G2. Here it's BN254 and Kropkin cycle of curve. We tell Nova that we want to use KZG with Pedersen commitments for this specific instance of the IVC that we are going to run. For the final decider, we say that we want to use the Ethereum decider with basically the same parameters almost that we are running the IVC in, which makes sense. So BN254 Kropkin, the same circuit, KZG and Pedersen. It's just that in the end, we will verify a final Groth16 proof because we know that it's going to land on chain. And this decider is going to be for the Nova IVC scheme. But later on, we will want the decider to be for other kinds of IVC scheme, such as Hypernova, Protogalaxy, etc.
So do you guys support Hypernova Protogalaxy or just Nova right now?
Just Nova right now, yeah. But we are working on the Hypernova. Yeah.
Cool.
So then you can basically just initialize Nova, run the IVC for the certain number of steps. If you have auxiliary inputs, that's where you are going to put them in the proof step as parameters to the proof step, to each of the proof steps. So if I go here and I check the proof step, you can see that the external inputs are supposed to be scalar field values of the curve that you are basically running the IVC on. It's not allocated FPVARs yet. So you will just provide the external inputs as scalar field values, and Sonobe will handle the parts of allocating them as witnesses. So you don't have to worry about initializing FPVARs. You just need to provide them as a regular scalar field values. So yes, it's just going to run the proof step. And once it's done, it's just finally going to run the final decider circuit, proving the Nova state that we have ended up with, and generating a Groth16 proof, running the relevant with the relevant Groth16 parameters. And the decider circuit will just verify that the proof is correct. And once the proof is correct, once we know that the proof is actually correct, we can actually verify it on chain. And that's what we will do by generating the decider template here. So it's the decider template is basically the Solidity contract that we are going to deploy on-chain to verify the final Zk-Stark proof. So we compiled the Solidity for that. We initialized an EVM, and we are just checking that. So this is just checking that the outputs of the call that we have done to the contract is 1, so meaning that the proof is correct. And then you can eventually store the verifier, the call data, and you can deploy the contract on chain and start to verify the actual proof on chain. So let's run this. I think we can run this. Oh, I'm just going to switch my screen. So yes, so here you can see that it's warning you that you are running with the light test feature. So that means that the final decider circuit for Ethereum is not the one that you should use in production. So it's an incomplete decider circuit. Yeah. So yep. So it generates the proof. It's verified that the proof generated by the decider is correct, and it will eventually store your solidity verifier on your machine. So we can go get it. So the final solidity verifier is quite a beast, but it's actually pretty straightforward to get. So it will basically check that the final folding step has been performed correctly. So that's the idea of this first part. Then it will also check that the KZG commitments have been, the KZG proof have been verified correctly. So it's here. So here it's checking that the KZG proof is correct because we are using a KZG in that case. And it will also check, so it will do 2 KZG proofs check and 1 final Groth 16 proof. So it's 2 KZG proof plus 1 Groth 16 proof. Yeah. So that's but it's actually a pretty cool cost as of today, and we can reduce that further in the future. But yeah, that's what we're going to do.
Look like roughly, because I remember like the original one that Jordi was working on at like something like 20 million Groth 16 constraints. How many constraints does this one have?
So sorry, can you repeat your question, Ayush?
So like the recursive Groth 16 proof, like how many constraints does that have? Like both like absolutely and relative to like the number of constraints in F.
So it's like 20 million and 20 million constraints, and let me think. Yes, I think it is dependent on F. Yes, it's dependent on F, but I'm not too sure about like what's like the what's the asymptotic of its dependence on F. Yeah, I'm not too sure about that. But yeah, as of today, the circuit is pretty large. Yeah. Does that answer your question? Are you sure?
Yeah, that does. And then the KZG calculation, that doesn't add much overhead on the recursive side because that's from directly from the Nova, or is that also expensive to compute?
Do you mean in the circuit or in Solidity?
For in Solidity, I imagine just verifying the commitment opening is not too many more constraints, but
No.
I guess I'm talking about like when you generate the proof itself, that KZG is like additional, like you're generating a Groth 16 proof and the KZG commitments. And so is that like quick, the KZG commitment generation, or is that, I don't really know how to think about just generating commitments versus.
We haven't benchmarked, to be honest. We haven't benchmarked that, so I'm sorry, I can't really say to you. Maybe Arnaud would be better placed to answer you that specific question because he implemented the decider circuit. So if you want details, I think you can poke Arnaud and he will have more things to say than me. Yeah. Cool. So yes, so the Nova verifier, the on-chain verifier, as you can see, wait, I'm going to change again my screen. I'm going to try to explain to you a bit more the contract. Okay, so the solidity verifier, you can see, takes as the first inputs of the call data the I value, so the number of times that you have done folding, Z0 and ZI, so the initial state and the final state. It also takes the committed values that are being folded within the scheme. So this is a detail, so don't worry too much about that. you have also the gross 16 points that you are going to use to verify the final gross 16 proof. So this is the regular gross 16 proof that we all know. And for that, we are just using the gross 16 templates that everyone is using, the gross 16 verifier of StarkJS. And we have also some KZG proof, as I said, that needs to be verified in the end. So the call data looks like this. So 10 is the number of steps that we have done when we were folding. So it's the I value. 3 was the initial value that we started with. And we end up with some final values that we want to prove for the final step of the IVC. And those then all corresponds to the points of the gross 16 proof and the points of the KZG proof that we will verify on chain. And yeah, we can deploy that contract and format the call data correctly and verify that that contract will verify the proof that we have is correct. So I think that's roughly what I wanted to present. Yep, I think that's the end of this quick little tutorial on Sonobe. Do you have any other questions?
I guess sorry, I'm not in front of you right now, but I guess for this to be useful for on-chain stuff, basically like the amount of constraints that you're computing needs to be like, or because there's like some number of million constraints in like this final decider. So is it basically true that like for this to be better than just doing everything 1.16 proof, it needs to be more than that decider size, basically?
That's a good question.
Are there other benefits that I'm missing of this? I guess there's like some dev tooling kind of benefits in that like you can be more agnostic to the number of steps that you're folding. Like if you're folding like sometimes 100, sometimes 50, then you can just have one circuit for that. But other than that, just for raw performance, I guess you need to hit like whatever number of million constraints for this to become better, right?
Yes, I think that makes sense. Yes. So in our case, for instance, where we fold 850K Bitcoin blocks, that totally like makes sense to have this final circuit. I think we are at less than 20 million though, but I don't want to say something wrong. But yeah, I do think that if you are able to like have a final circuit that is less than this final decided circuit of X million constraints, then it does make sense to not go through all those steps of folding and generating this final proof. Yeah.
Makes sense. Yep. I think we're good.
All right, cool. Yeah, if you have questions or whatever, I'm available. We'll be happy to help you. And yeah, so that's it.
Cool. Thanks so much for your.
Thank you, Ben.
All right, thank you. Bye bye, guys. Enjoy.
Bye.
Bye bye. See you.